Alright, in this video, we will be uh, discussing free body diagram. Um, my discussion, based on my understanding, is going to be um, based on answering these problems. So, uh, in a free body diagram, we're told that we don't need to include the magnitude. This is the number value. Um, we do have two things before we start. Just want to make something clear on the difference between scalar and vector. I believe I've already mentioned about these two things in the previous videos, but let me just give you a basic distinction between the two. So for scalar, this is magnitude without direction, so it's only magnitude. For vector, it's magnitude with direction. So what are examples of vector quantities? We have, let me just show you. I know this source from NASA, scalar versus vector. Although it's not easy to digest in the first place, I suggest you base your memorization on this first. It's pretty easy to understand. This is from Organic Chemistry Tutor. So for vector, magnitudes with distance, with directions, are basically displacement, velocity, force, and acceleration. For scalar quantities, we have distance, speed, mass, and temperature. So yeah, just think about it. The things that are under scalar quantity, they don't have a direction for themselves. For instance, temperature. You can't say northeast, south, or west in temperature, right? So yes, temperature is scalar. For vector quantities, these have a direction. So, with that made clear, let's start on the free body diagram. We now know what the magnitude means. It's a value. In scalar, it's only the number itself, and for vector, it's a value that comes along with a direction. So, yeah, creativity, I won't really be that creative. The important thing is I'm able to illustrate the object. So let's say this is the book and it's at rest on a tabletop. So this is the surface of the tabletop. We have to show 4 forces in a free body diagram. So I believe this is the applied force, or FA. The one at the back is the frictional force, the force that is against applied force. And the one going above is, I suppose, the normal force. The one going down is the gravitational force. On Earth, all objects are subject to being under the force of gravity. So yeah, it's natural to have gravitational force pulling the object down. In engineering, there are many things that are applicable in this general concept. Say, an object is suspended. Say, there's a hook here, and this is, I'm not sure what this is called, but it's the thing that, I'm not sure what it's formally intended for, but yeah, I think it's called a crane. Something like that. And there's a weight here so that this part will, so that there is a proper distribution of weight. And there's a string here, a really strong string, perhaps a heavy duty rope. And there's a hook here. It carries a concrete object, and yeah, gravitational force pulls the object down, but because the capacity of the rope to not break is stronger than the weight of the object itself, then the normal force is pretty strong. It's able to keep the object from falling. So yeah, another application of the free body diagram is, say, you want to decide if you want to push an extremely heavy object without wheels or place it on wheels. It's a lot easier. We all know that wheels are a form of a simple machine, if I'm not mistaken, and they make pushing objects to from point A to B easier. Of course, the wheels should um, be strong enough to uh, traverse on roads. Depends if it's going to be rough or smooth, but anyways, we do have the applied force. This is any force that makes us move the object, and the frictional force is the one that keeps the object from moving. So if the frictional force is greater, I mean, if the object has a really high value of mass, then if the applied force is not strong enough to overcome that weight or mass, the frictional force is then stronger than the applied force. I suppose that's the way you explain it. So a book is at rest on a tabletop. Let's see the answer key. Ooh. I'm afraid my iPad RAM is pushed to its limit, but yeah, this is what we have. We have to write these values, summation of fx and summation of fy. So two more formulas you have to remember. Summation fx, I suppose this corresponds to the horizontal aspect of the free body diagram. So it involves the FA and FF. So FA minus FF. And then for the summation of F of y, or Fy, this is the normal force minus the gravitational force. Let's see if it's correct. So yes, so far so good. In the answer key, the frictional force is abbreviated as only a small f letter. But yeah, you can, either way, it's the same thing, even if you write FF. Also, yes, I suppose it's advised for one to just write a small f to symbolize the same thing. And by the way, gravitational force of gravity can also be abbreviated as W, or the weight of the object. So normal force will be written as N, and then the Fg will be written as weight. And then Fa, yeah, we just write Fa. And then frictional force can be written as F only. Okay, what else do we have? Okay, we have a chandelier. Let's say that this is the chandelier. This is the platform where it's suspended. So we have the weight, we have the normal force. So summation of Fy is equal to the normal force minus the weight. Now, is it correct? Well, why is it 0 newtons? Okay. I believe the T stands for tensile strength. Instead of a normal force, we write a T instead, since, yeah, a chandelier, this kind of example involves some form of rope or string that keeps the object from falling down. So in this case, it's a chandelier. The chandelier is suspended from a platform that's from above. So yeah, I believe it is going to be 0 newtons in the scenario where yeah, the object isn't moving, I suppose. So it's just suspended from above, and yeah, it makes sense to say that the summation of Fy is just 0 newtons. If it's not 0 newtons, then it should be either falling down or it's actually, if the tensity is stronger, or the tensile strength is stronger than the weight, higher than the weight, then I'm not sure what it is supposed to mean. Let's move to number 3. When an egg is free falling from a nest in a tree. So, okay, I won't draw a box anymore. So this is an egg. So falling from a nest. Let's say this is the nest. And I'm not sure if we're supposed to write applied and frictional force. The egg is mid-air, so I'm thinking this is supposed to be the normal force. This is the weight. So summation Fy is equal to N minus W. What does the answer key state? Okay. Yeah, we don't write a normal force. The object is already falling, and so the normal force is non-existent. The only force that's pulling the object down is the weight. So it's, wait, is it T again? Okay. T minus W, such that T is non-existent, therefore we only have W. And yeah, it's gonna be a negative value. Negative means down. Yo, what is going on? Okay, I'll have to refresh the app for a while. Okay. Negative means down. The object is going down. So, for number 4, a hang glider is gliding through the air towards the ground. So we have to include the air resistance. I'll just draw the hang glider as a box. Gliding through the air towards the ground. So there has to be some action in terms of the Fx, that is the applied force and the frictional force. But then there's no friction. The object has no contact with the Earth's surface, so I'm not sure if f of a and f of f are involved. But for sure, since there's gravity that pulls the hang glider down, even though it's able to glide, it just basically slows the speed of falling. But then yeah, there is action in the x-axis. We're just not sure about what we do with the friction. So this is the weight. Well, we don't have any strings attached from above, so air resistance, what does that mean? Okay, so if we ought to include air resistance, then this object particularly is a hang glider, so it's able to resist the pull of gravity significantly in comparison to other objects if they were to fall down. For instance, a heavy metal cannonball. Compare its rate of falling with a hang glider. So there is some sort of T. So Fy, summation of Fy is equal to T minus W. Well, we don't write it as T, we write it as AR. Okay. So far so good. This is air resistance. And what does it say here? Okay. Yeah, it does make sense that the weight is still greater than the air resistance that the hang glider is able to showcase. Since eventually the hang glider will reach the ground. If the air resistance that's being produced by the hang glider is greater than the weight, then the hang glider is better off just suspended mid-air for the entire time, because it will never reach the ground if the weight is not bigger than the air resistance. So okay, what else? Summation of f of y is not equal to 0 n. How is that justifiable? Well, there is a difference. The air resistance and the weight will never be equal to each other. So if you subtract them, it will never equal to 0. So it makes sense that summation of Fy is not equal to 0 newtons. So this particular expression, I suppose, or inequality is associated with the idea that the falling object will eventually hit the ground. So somehow, if we were supposed to also include the air resistance in example 3, then it's the same idea. The weight will always be bigger, but then at the same time, the hang glider will take more time to reach the ground, since its air resistance is quite bigger. Summation of Fy will have a negative sign. That is true. Okay, yeah, we just answered these. Let's go with number 5. Include and ignore. Okay. A rightward force is applied to a book in order to move it across a desk with a rightward acceleration. Okay, so we do have applied force. And we have the friction, rightward acceleration, and then we have the weight, we have the normal force. The book is on a desk. Let's say this is the desk. And we are ignoring air resistance. If we ignore air resistance, then I suppose we eliminate Fn. What does the answer key say? If an object is falling and we ignore air resistance, then we don't write the force that's going up at all. But then, even if you ignore air resistance and the object is on a surface, I suppose you still write it. So, normal force over there. Alright. So, for the summation fx, so fa minus f, for summation of fy, that is fn minus w. For Fy, it's equal to 0 newtons. I think this is justifiable since the object isn't either falling or being lifted above. So yeah, it's understandably 0 newtons. How about the summation of Fx that is said to be greater than 0? And why is that? Let's read the instructions again. So a right-wide force is applied to a book in order to move it across a desk. So in order to move it, a force that is stronger than the friction is applied. So we're thinking that the object has already moved, and therefore the applied force is greater than the frictional force, which makes summation of Fx greater than 0. If the weight is big enough to withstand the applied force's intent to make the object move, then the summation of Fx will be less than 0, which is a negative value. But then yeah, summation Fy is going to be always 0 if the object is, say, on a table. It's not falling or it's not being lifted. Let's go to number 6. College student rests a backpack upon his shoulder. The backpack is suspended motionless by one strap from one shoulder. Okay, so let's say these are the two straps. Well, the pack is suspended motionless by one strap from one shoulder. I think we could get somehow creative here. Let's draw a bag. It's not a perfect square anymore, but yeah. The scenario is somehow something like that. And there is T as the force going up. Force going down is weight, the weight of the bag. Do we have applied force? Do we? I suppose not. There's not enough textual information that suggests we have to write for FA and FF. Besides, the backpack isn't sitting in a surface, so yeah. Summation Fy T minus W, it's 0 newtons. The bag is not falling, it's not going up either. Although realistically, if a college student starts to walk, then the backpack could somehow go up or down. Let's see what the answer key says. Yeah, what I said was right. Although we could have just settled for a simpler illustration. But yeah, it's the same thing. Alright. A car is stopped at a stop sign. So this is relatively simple. Let's say this is the car. We do have applied and frictional force. We have the weight of the car as well as the normal force. So summation of Fy is equal to Fn minus the weight. The car isn't falling, it isn't being lifted either, so this is equal to 0 newtons. The summation of Fx is equal to Fa minus F, such that a car is stopped, so this has to be 0 newtons by the moment the car stops. But if it hasn't stopped, the Fa is supposed to be bigger. And then yeah, why did I have 0 newtons instead of Fa being bigger? It says here the car is being stopped, so yeah, the present tense is stopped, so yeah, both are 0 newtons. Exactly what was mentioned. Okay. What else do we have? Okay, now we're going to have some specific values, and yeah, we're gonna mix free body diagram with it. We're gonna use the same methods to solve the problems. So, a loaf of bread weighs 5.3 newtons on Earth. So, weight is 5.3 newtons. What mass does it have on Earth? Sorry about that. The normal force is do we know that? Okay. So we do have to integrate the formula. The weight is equal to mass times the gravitational acceleration, or W is equal to mg. You don't confuse it with W is equal to Ft. This one is for work. Force times displacement or distance. They're essentially the same thing in certain scenarios, but one is vector, one is scalar. That's one difference you have to consider also. And yeah, the answer key didn't write the three other forces, only the weight. We have 5.3 newtons, and we're looking for the mass. So gravity is 9.8 meters per second squared. That's always a standard value. 5.3 over 9.8 is what? That is equal to 0.54082 newtons. Wait, what is the unit for mass? The SI unit for mass is kilograms. I'm not sure if this is kilograms, but by standard, oh yes. So if you're not sure what unit to put, just make sure that it is the SI unit. So yeah, the SI unit for mass is kilograms, not grams. For meters, sorry, I already said it. The SI unit for distance is meters, not kilometers. Just to be clear on that. Alright, so yeah, oh wait, I've already shown the answer, but let's see if you can solve number 2. For number 2, the same loaf of bread is now on the moon. The acceleration due to gravity is 1/6. Okay. Okay. So on the moon, the gravity is just 1/6 of the Earth's. So let's say 9.8 meters per second. That is the gravitational acceleration on Earth. Multiply that by 1/6, and then we'll get the gravitational acceleration for the moon. 9.8 over 6 is equal to 1.63 meters per second squared. Let's see if that's actually true. Gravity acceleration moon. Precisely. So 1.63 meters per second squared, that is the G. I wonder what's going to be the weight of the object, of the bread, since it's definitely not going to be 5.3 newtons. I'll tell you this. The mass of the bread, regardless of where it is in the universe, if it's always going to be the same, but then the weight can be different. The weight and mass can be the same on Earth, but in other planets, the weight will be different because the gravity is different. The strength of the gravity. Say, Jupiter. Although it's a gas giant, the gravity is really strong. You'll actually get pulled all the way to its core, and that's not really a pleasant experience. According to what I remember, only after 2 seconds you die, the moment you start being on Jupiter. If that happens. Although it's not, yes, it's not realistic. It doesn't, it's not in accord to theoretical ideas, but yeah, if that just happened, let's see. I'm actually curious, how long before you die? Well, yes, there. Uh, I said 2 seconds, I suppose, a while ago. It's actually in less than 1 second you'll die already. Yeah. The pressure is really big, so especially in the red spot. So without a suit, a person could survive for 3 minutes. What is ebulism? Hmm. Uranus is pretty beautiful. I like the color. Alright, that's it. What mass does it have on the moon? What would debris weigh on the moon? How do we solve this? So W is equal to mg. We have to look for the weight of the bread on the moon. Yeah, the mass of the bread on Earth is the same as the mass of the bread on the moon. So for letter B, mass is still 5.3 newtons. What's different is the answer for letter A. We have to look for the weight of the bread. So weight is equal to mass. The mass of the bread is 5.3 newtons. And the gravitational acceleration is 1.63 meters per second squared. What is the SI unit for weight? I suppose that is newtons. Gosh, I hope I'm correct. So the weight is 8.639. Does it make sense? What does the answer key say? Okay, I take back what I said about on Earth, the mass and weight can be equal. Just to play it safe, they're not equal. So we know that the mass of the bread on Earth is 0.54082. That's the value we multiply with 1.63. Okay, so kilogram times meter per second squared. I suppose that's that results to the unit Newton. 0.54081 6 times 1.63, that is equal to 0.88153 newtons. So what is the mass on the moon? Did I get it right? Well, yes, yeah. As you can see, it's the same mass. It's just the weight is different. Okay, so the mass of an object deals with compactness of atom. Okay, mass is not affected by gravity and the gravitational acceleration. Okay, that makes sense. That's the reason why mass is the same, regardless of what planet the object is located in. Okay, so let's move to number 3. On Jupiter, the acceleration due to gravity is... Okay.